Sí, cierra. Okay, so now we're going to start into the streaming. We're streaming now over YouTube and LinkedIn Live, and the meetup is going to be a hybrid from the Polytechnic University from Valencia, Spain. And we are relaunching the community. I think more or less the last meetup was 2 years ago. And for today, we have with us Ángel Encalada as a speaker, and he's going to show us some fundamentals or the first steps over the platform, over the Confluent fundamentals. I think more into the Kafka, into the event management platform, because Confluent is a ecosystem that allows us many more things, but for today is focused on the event management. Ángel Encalada is a integrations engineer. He works at Minsight, an Indra Group company, and he works with many different clients in different platforms, and one of these platforms is Confluent. So, come on, Ángel. Good afternoon, and when you want, you can start and I'm be taking a look about the chat if anyone has some questions.
Okay. Hi everyone, I'm Ángel Encalada, and today we will talk about Apache Kafka and Confluent Platform, or for those who want to learn or consolidate basic concepts related to these technologies. The content of this meetup is based on learning the basic concept of Apache Kafka and Confluent Platform, such as events, topics, producers, consumers, partitions, brokers, schema registry, replication, and other related concepts. Additionally, a small demo with a Confluent Platform locally using Docker. About me, I am a software engineer with more than 13 years of experience in the
Ángel, could you hear me?
if they missed the call. So
Okay, Ángel, we lost you, I think, a couple of minutes.
I use my mobile phone with as
Okay.
a webcam because now I receive the call. But well, about me, I am software engineering with more than 13 years of experience in technology information sector. I have training certifications and experience in project management under PM book. And experience in project management and Scrum approaches. as well as in business processing modeling and implementation. Or no,
Okay.
I come back. Well, um, um, event-driven or architecture, EDA, with Confluent and Kafka, business intelligence and methodologies such as Lean Six Sigma, UML Group, Deal. I also knowledge in relational and non-relational databases and software development in technologies such as Java, PHP, Visual Basic for application, Angular. In summary, I have seen different technology through my professional journey. Relate to today's talk, I have participated in about 4 projects with Apache Kafka and Confluent technology, including installations, event governance, software development, and integrations. Um, Today, talks intend to serve as a foundation or a starting point for those who want to learn or consolidate basic concepts related to Apache Kafka and concept Confluent, such as events, topics, partition, broker, producer, consumer, replication, schema registry, and many more concepts. Additionally, we will finish with a small demo with Confluent Platform on our local machine, running images or service from Docker. This way you can replicate this demo later if you wish to do so, since it doesn't require to use the use of any paid account or license. If you want a more extensive official and clear learning path for later, you will find all of that conference documentation in the next link. Uh, well, and if we go to Apache Kafka documentation, it says that Apache Kafka is a distributed streaming platform. This means that Apache Kafka can be used to create one or more real-time data flows, and it can be used to process these flows and produce results in real time. Uh, so let's start by define with an example that Apache Kafka is and some of these components. Let's suppose you have a smart electricity meter at home that generates data related to the load every minute. This data somehow goes to a Kafka server. Thus, the Kafka server continuously receives data every minute from a smart meter. Similarly to this same Kafka server receives data from other meters in your city. And all of that arrives at the Kafka server, resulting in a continuous flow of real-time data. Now, once the data has arrived at the Apache Kafka server, an application has been created to read and process this data. This application can be doing various things, for example, calculating and monitoring the global electrical load of each household. When the load exceeds a predefined threshold, it sends a message to the home owner to alert them. This type of alert, perhaps as a message, makes no sense after an hour. It's urgent. that these types of alerts occur in a seconds or at least in 2 or 3 minutes, right? So the application is not accumulating data and analyzing it slowly, but rather is continuously listening and processing as soon as data arrives at the server. This is the what is called real-time stream processing. So Apache Kafka is highly scalable and distributed platform for creating and processing streams in real time. How does it work? In the previous example, Kafka adopts the pub and sub messaging system architecture and functions as an enterprise messaging system. A typical enterprise messaging system has three components: producer, message broker, and consumer. The producer is a client application that sends data records. These data records are called messages. The broker is responsible to receive messages from producers and store them in locally memory. And finally, consumers are again client applications that read messages from the broker and process them. In this architecture, the broker is in the center and acts as an intermediary between producers and consumers. In the smart electric meter example, the left part the left part uh, is a producers, broker, and consumer. How did Kafka organize if borrowed from Jake Clip's blog? We lead the Kafka project at LinkedIn and is now the CEO of Confluent. The, the diagram explains in the data integration problem in a company where all the boxes are different and reflect application backends and generate and store data. However, data generated by one application is often also needed by others. So all these arrows shows the movement, the data between source and destination application.
This is important because it's not the typical synchronous integration. That is an integration about events. That is the reason you could have multiple application generating data, and you have to store all this data, and you could manage this kind of data. You could have many different partitions, and you could have many different customers with that consumes different kind of topics. That is I think a concept that we're going to take a look in a few minutes, but is really interesting because in our experience, all that big companies use this kind of platform because have to manage lot of data, a lot of ingestion, and you have to manage all these kind of things. In the slide, you have the IoT ecosystem. Is really clear that all this sensoring is generating lots of data to have to process.
Yes, there's a big problem when the producers and consumers join in a uh, organization and conversation the or share the data, different data for as applications. In growing organization, this relationship keep growing. Eventually, you'll need app in a situation like this where maintaining this relationship is almost impossible. LinkedIn tried to solve this problem using the PAP and SAP messaging architecture, and the result was the following. They places an intermediary in the middle, and some applications began to function as producer or consumer. This architecture offers many advantages and simplifies the solution. How has it evolved from data integration solution to a streaming platform? Kafka started with two things: server software that can be installed and configured to function as a message broker, and a Kafka-based client API library to help with the following: creating Kafka producer applications and creating Kafka consumer applications. But later, Kafka aspired to become a complete real-time streaming platform. And to achieve the goal, they added three more components: Kafka Connect, Kafka Streams, and KSQLDB. Kafka Connect and Kafka Streams remain open offered by Confluent as a commercial tool. So Kafka evolved as a set of five components: Kafka Broker, which is the central server system Kafka client app, which are the producer and consumer API Kafka component, which address the initial data integration problem for which Kafka was originally designed. Kafka Stream, this is other library for creating extreme real-time processing application. KSQLDB, where message or stream transformation are addressed as if it were a real-time database. In summary of for this section, by adopting the PubSub architecture, Apache Kafka becomes the system where data flows, producers can send data as messages to. Kafka brokers as soon as an event occurs, consumers can consume message from the broker as soon as data arrives. Those, produce, those producers and consumers are completely decoupled and don't need tie couplings or direct connections. Producers and consumers can be added, removed, and modified as business use case evolve. Even an event is a fact that occurs at a moment, something you want to capture and share with other parts of your system. Think of business and system events like payment authorized, payment failed, order shipped, or operational events like the smart electric meter reading example, which can have data like device ID, value, timestamp. From these examples, we summarize that something happened, and we want to record uh, an event is visualized as a record with three components: who or what is about, what happened, and when it happened. In Kafka documentation, you will often see described as a key, value, and timestamp. You can store this record in a schema such as JSON Avro or protobuf in the case of Confluent. And the point is that the event is a durable and ordered path that other parts of the system can read to. The most important mental shift is that events are immutable. Ay, perdón. So, in sample words, once an event is written, is not edited. If something changes, you write a new event that describes that change in Kafka. You append new facts, you don't go back to update previous one. This advantage means you can reconstruct a state from history whenever you need to. Thus, auditing the history as a sequence of facts inside of single current value that trace previous one. This is why Kafka differs from traditional database-centric architecture.
And this is a thing that impacts directly in the business, because you use or you design architectures over Kafka, over Confluent, about all these things, because you're going to have different scenarios when you have to collect all the things that are going to happen, not the last event, not the last record, but all the story is going to
The
happen.
event will, the
Yeah.
event will not be deleted once it has finished or consumed. Mm. Well, when you yourself so is an event just a JSON message. The answer will be an event is a message with meaning and a contract. The contract is what allows multiple teams to build producers or data sources and are consumed by consumers or scenes. Later, we'll see who schema registry helps makes that contract verified and with respective versioning, since the contract can change over time. Finally, it's worth mention that Kafka enables and changes how systems evolve. Replay. Kafka is not a queue where the message disappears when it's read or consumed. Kafka is a log where multiple independent consumers can read the same stream at their one piece without interfering with other consumers. Of course, the real world is messy. There are retries and there can be duplicate events. So later, when we talk about consumers, we'll mention these cases and who Kafka designs consumers to be safe in delivery with properties like at least once. But first, we need a place to put events. That's where we need the diff of topics. Topic is the main container for events. A topic is category plus history because it reminds you that you are not just routing message but storing a timeline of events. So you could have topics like orders create, payments authorized, inventory reserved. The name is not a cosmetic detail. Names communicate to the owner the intent of creation and later influence who well the topic can be governed in the platform. Conceptually, Kafka topics are blocks, not queues. In a queue, a message is consumed and lost. to all other consumers. In a Kafka topic, you can read without deleting those events, remaining available as long as the topic retention policy allows. That's what enables multiple independent consumers on the same stream, and that's what enables replay. When you look at a record inside a topic, it was some important parts. Conceptually, it's a key value pairs plus a timestamp and optionally fields. This value, the value is the payload. What happened? The key is optional, but when you decide to use it, it becomes a very powerful design tool because it affects partitioning, ordering by editor, and also log conversion. The timestamp is the when, depending on the configuration, it can represent when the producer creates the record or when the broker receives it. Topics have a life cycle and police cycle. Kafka is not a database, and retention is not forever. By default, you normally configure retention by time and or size, and that
No, I think when you subscribe to an event, you are subscribing for you have to identify the topic you want to subscribe.
yes, you
Okay,
subscribe or consumer group can subscribe to a topic
okay,
or or two or three topics. It depends. No only group consumers um, one topic.
okay.
No, it's multiple. Yes. Mm, you normally configure retention by time or size. Um, Summary Kafka topics are powerful immutable logs that allows you to store process and replay a stream of events reliable while keeping full historical context intact. The topic doesn't have a unit of order. Order is a property of partition within a topic, and that's the next section. Partitions are the mechanism that makes Kafka a distributed system and not a single large log on a single machine or node. If a topic lives entirely on a single location broker, the maximum size and throw part of that topic will be limited by the broker's disk and network. Partitioning solves this by dividing the topic's log into several smaller logs. Partitions that can be placed on different brokers, who does Kafka decide which partition a record goes to. By default is determined by the record's key, managed by a hash function and mapped to one of the partitions. Conceptually, the hash of the key and modulate by the number of partitions. The implication is very important. The same key always falls into the same partition, which means you get ordering for that key. That key. Choosing the key is a design decision, not a minor detail. If you key by order ID, then all events for, for an order are ordered. If you key by consumer ID, then you get a timeline per customer, but you also risk hotspot when one customer generates much more traffic than others. If you don't provide a key, producers can distribute records among partitions in a round robin. algorithm.
For now, we're going to the 6, 6:30. Uh, I don't know if you have more or less the timetable for the split the workshop.
Yes.
Okay, you are going more or less okay with the speed.
Okay. Well, finally, partitions are the unit of parallels on a consumer side. Consumer groups can process partitions in parallel, but at most one consumer within the group will read a partition at a time. That's we. That's why the number of partitions becomes the parallel selling for a consumer group. You can add partition later, but it's not free. When the number of partitions change, the key partition mapping change and some keys move. More partition can mean more parallels and throughput, but also more overhead. Each partition means more files on disk, more metadata to manage, and the more work during rebalance. For the demo, we'll apply the simplest approach, but in a real clusters, you normally choose the number of partitions based on spec read parallelism and key distribution. Then adjust when you have actual event traffic. Now the question, where do partitions live in the broker? Brokers are the actual servers or instance of Kafka cluster. So it's correct to say that a group of brokers forms a Kafka cluster. Brokers store partitions, handle produce request writes, handle fetch request reads, and participate in replication. When data is written to a topic, they get data directly from the partition on the broker, where is stored. This distribution across multiple brokers is what allows Kafka to scale massively while maintaining with high throughput. Within the cluster, there also a control plane role that coordinates and manages metadata and leadership change or coordinate change. Kafka Science version 4 use Graph, Kafka in Graph mode instead of Zookeeper. Practically speaking, each partition has exactly one leader at a time, and brokers cooperate and elect leader perform failover when a broker goes down and maintain a consistent view of the cluster state. Replication is the durability and fault tolerance mechanism that Kafka has if you store each partition on a single broker. Because this fail, machine fail, there are network partition, etc. Replication fixes by maintains multiple copies of each partition on different brokers. Each partition has exactly on one leader, replica, and one or more follower replicas. All writers go to the leader and followers continuously fetch from the leader and thus store the same record. The replication factor indicates the total number of replicas or copies that Kafka maintains for each partition. Another important term that is widely used is ISR in seeing replicas. In simpler words, ISR is the replicas that are currently up to date and safe to rally on for a read. If a follower slows down or disconnects, the ESR shrinks. When it recovers and catches up, it can rejoin the ESR. The matters because what you consider committed depends of AC On the producer side, ACCAS controls how many acknowledgements are required before the producer considers a write successful. In simple words, how many updates you wait for. With ACCAS equals 0, you don't wait for any confirmation. This makes it fast but unsafe. With ACCAS equals 1, you wait for the leader to write on the leader, but followers may not have to yet. With ACCAS equals all, you wait for write confirmation from the leader and followers, ESR. Uh, Now we'll move on to see the client that writes data to those partitions, the producer. Producer is the client that adds records to a Kafka cluster. In other words, to the partition of a topic. As we've seen previously, the producer sends the records to the leader of partition, and a Kafka stores it in partition block. Consumers, they are the clients that reads records from the partition of a topic. Consumers can be application or service that subscribes to one or more topics and process events as they arrive. Within a single partition, consumption is sequential. Records are read in order according to a concept we call offset. So the offset means the position that makes reading possible. The checkpoint. This ensures that if the consumer disconnects, it can consume readings from where it left off. These offsets are committed in Kafka and stored in an internal topic. If a consumer fails and restarts, it reads its last committed offset and continues processing without losing data. To scale processing, consumer groups exist. Consumer group, um, all consumers in the same group share the task of reading the partition of a topic. Kafka assigns each partition to a consumer in the group. No consumer in the same group reads the same partition. This enables parallelism. Um, Schema registry is a contract and evolution or version. Schema registry solves the integration problem between the producers and consumers who need a shared contract to write and read data in a topic. As a more consumers start reading topics, sometimes writing by different teams or even completely different departments. It's essential that they understand the data schema they receive. If the team sending data producers data fails, renames a label, or change data type, and the consumers isn't updated at the same time, things break, like subtly parsing errors or investigations of why is the JSON different today.
So the schema registry is by the way, as it as its name, where you register different schemas, and between producer and consumer you are working on only one schema. So when you move some data, or you publish some events, you always match with the schema ID, because this is the contract between the both.
Yes,
Okay.
the concept is a version. If you create more or edit the schema, you replace for a new version. No?
So this is the way I think the platform or the ecosystem uh, enable uh, to improve the integration because as you said you could uh, version different schemas so you can evolve different data structures and the system is continue working. The last release and 2 3 versions ago is all this is working okay because the different versions are designed for different business needs and different producers and consumers. Okay,
Yes.
okay.
In the next slide, I it talk about the schema registry supports compatibility rules that help manage the schema change appropriately. Forward compatibility. All consumers can read message generated with newer schema from producers. Backward compatibility. New consumers can read message generated with older. And full compatibility is maintained both forward and backward. Um, these rules are a fundament for designing who change are implemented. For example, if we control the producers and update them first, we could opt for forward or future compatibility with consumers that we don't necessarily control being able to update later.
And as an integrations architecture, I think it depends of the client.
Yes,
It's a business decision if you want to which part you want to control better than other. Okay.
yes, you decide
Mhm.
the schema, uh, they configure the compatibility type.
Mhm. Okay.
In
But
schema registry in Confluent,
more
yes,
it's more common is usually to have the full type.
yes, it's more
Okay.
um, it's default decision and um,
It's more
it's
work because big I think big effort for the engineering team, but is the best compliance.
the schema registry in Confluent is adopt three schemas: JSON schema, Avro schema, or protobuf schema. Only these three formats for used for Confluent in schema registry. Well, I finished all the concepts. um, well, the live demo produced. Mm, well, um, for the demo, as prerequisites, we need to have Git and Docker. Um, I have the Git version 2.2.3.1.
Any kind of I think any kind of different stuff you use for the workshop for the demo.
Yes,
Uh, I
use
will
Git version.
I will share all the links maybe in the YouTube channel in the comments of the streaming. I will share all the things.
Yes. Well, uh, is a prerequisite for reproduce this demo. Well, I download a Git version and Docker Compose uh, with Docker desktop. Sorry, uh, install locally, which includes Docker and Docker Compose the commands. Well, first, we will clone from the official Confluent repository is necessary for this meetup, and bring up the Confluent services from the YAML Docker Compose. Um, is a YAML file when the service is broker, schema registry, connect Prometheus for statistics reports, alert manager, control center is the main UI in Confluent, KSQLDB for manage the streams such as tables. REST proxy flying is a new form to manage the streams. Flying job manager, flying task manager. Well, is the Docker Compose to uh,
This is the basic you have to configure it. Okay.
yes, the basic configure, which includes all components of service in a single configure file. Well, um, to do this well, we will write the following command in our PowerShell: git clone this address. And when I have already executed the first command to avoid waiting for the download, now we will navigate to the path where is the YAML locate in my local system. Okay, this. Um, with the following Docker command, we will bring up all the Confluent Platform service described it in YAML. Once all service started, we can view the control center in the browser. Example. Well, it's the principal UI in Confluent. This is where you can create topics, launch connectors, monitor the cluster, execute KSQLDB queries, etc. Enter your cluster and create our first topic. In topic section, first, all create topics will be listed, and we just click on a button where it says add topic. Then we will create a topic named orders with 3 partitions and with default settings.
Could you focus, Angel? Could you focus the screen for look better the different
Ah,
fields?
bueno. First, I start the components describes in a YAML. When the components started, you can go to
No,
control center.
it's only the thumb
Mm,
at the screen,
yes.
only for take a better look at the fields. Okay, thank you.
Mhm. When the components started, you go to control center homepage, right? And then click in the control center name, cluster name, sorry, and then click in the topics for view the list of topics in these clusters. Uh, I created a topic with name is orders. Um, well, to create a schema for these topics is available in this section. We go to a schema section of our topic, select the topic, and then click in schema. You select if you create a schema for value or key. In this example, I create a schema for value and set a schema. I create a schema previously and copy the schema. Paste, paste this schema. Uh, Type record, name the record order, these files, order ID, customer ID, amount, currencies, and typical basic example. It's all for create a new schema for value. I'm clicking create. Well, this is the topic. My topic is orders. The schema is this. For default is currently put US dollar. Well, the next step in this demo, I will produce some message, but first, when we can see all the schemas available from the API. Uh,
So it's for taking a look over the full end-to-end integration, I think.
yeah. We can see orders value is a schema recently created recently. Then for our schema, we can see the versions it has with this command. The name of topic. Plus versions. Well, this schema to have two versions, and finally see the schema structure version and traditional data. Additional data. Sorry. Versions. So this is a Avro schema type. This is the schema. This is the subject, or ID the schema. Now we will produce message from PowerShell because Control Center produces a message as a plain JSON, such as a string, not as Avro schema. With PowerShell, all you have to do is edit the command by escaping the double quotes.
And is there any kind of restriction about the schema type? Because we could use different. We could use the free. I don't remember exactly. Buffer, Avro, and JSON is the same,
Yes,
or
it's the
it's
same.
okay. You are,
It's,
here
it's, uh,
you use Avro, but it's not any kind of special decision. Is
no,
the
it's,
okay?
yes. You can use free schemas
Okay.
in only free schemas in Confluent. Well, with this command, now will you produce a message, um, change the topic because I copy pasted this command. Well, well I add uh, now we see that it lets us write our records in the schema. We register uh, one order, maybe two orders, and three orders. If we can see the record in our topic from the control center UI, topics, orders, and such. Well, this three message view in the topic. Well, offset is a number of use the round robin algorithm for distribute the church because when they create the topic, I put three partitions. Once these messages are written to the topic, we can create a new PowerShell window to execute the consuming of message from the topic with the following command. It is if necessary to create a consumer group for consumer the message in a topic. You can see three message is the same that three message to produce. We see that the writing message are consumed and it is listening for incoming message. So if we add a new message, for example, it's a new message. Once added, we see how it updates automatically in our consumer. Oh, sorry. And put new record automatically. In our consumer group, this will be a demonstration of the definition of stream processing in real time. Another interesting test in this demo will be creating a new consumer group, and we will see that it consumes all the message in a topic, even though you have already been consumed by another consumer group. This demonstrates that Kafka is a log and not a queue, where once messages are consumed, they are not longer available to another consumer. Well, create the second consumer group. Um, Create a second consumer group to consume the same topic. We will see that indeed all messages are displayed. With this, we will conclude our small demo, which demonstrates the basic concept we have been discussing in the meetup. And at the same time, we will conclude the presentation. Thank you.
Okay. So in the last step, we could see how the second consumer is receiving the data. Okay.
Just consumer all the records is
Okay. Yeah, yeah, yeah.
independently.
I just see the group ID. Okay, that is
Yes,
the identifier. Okay.
because the Kafka is a log, a queue.
Any question about the workshop? So thank you, Angel, for the speech and the workshop for today. It was a beginning level, an introduction to the power of Confluent at the platform, and well, we have to plan the next meetups and share more in deep the Confluent platform. Thank you very
Yes,
much for you to come today. See you at the next meetup. Bye.
thank you. Bye.